spectacular natural areas in all of the world. Not really, but it's a place that we're going to come up to do this week's lab, where we're going to be studying ecological succession. Succession, as defined by ecologists, is an area of community ecology that evaluates or examines how communities change over time. And the concepts are rooted in the idea that communities change in very predictable ways. So for example, the term primary succession is a term we apply to moments where ecosystems start from bare rock. So say for example the Hawaiian Islands, a volcano explodes, bare rock is all that's left. Plants begin to invade that habitat to recolonize the land. That's primary succession. Here's an example of what we call secondary succession. I'm standing in an old abandoned field on the ski hill. As a matter of fact, this used to be part of the ski slope. It was abandoned 20 or so years ago. These trees weren't here 20 years ago. These plants weren't here 20 years ago. It was a nice mowed lawn. But they're coming back. The forest is slowly beginning to reclaim this field. There's a predictable way. There are early stage things that come in, weedy plants, these members of the aster family, milkweeds, they slowly come in. They establish shade and soil. Next comes in are the white pine and spruces. They are like these bright open habitats. And then they give way to mature forest. But there's always an intermediate stage, which is called an ecotone. As you move from an old field into the forest to the edge, you'll see an ecotone. If you'll look over here, you see the ecotone beginning to form with all those shrubs and bushes. And then it will eventually grow up into a forest like you see behind us. Unfortunately, this forest you see behind me is a planted forest, but we're going to get into some forest a little bit later on that are more mature. I'm going to go over here and take a look. So here we are now up in the actual Colgate Forest. The forest that surrounds me is probably around 50 years old, and we know that because this entire area at one point was an actual field. This is all a secondary regenerating forest. And if you look around me at the trees behind me, for example, you see there are all sorts of different sizes, different heights, different diameters, different species. Bark textures are different. Lots of differences in here. This is an entire forest community that is evolving together. We've moved from that old field into something that's a little bit older, a little bit less disturbed. You know that this was an actual old field because if you look behind me here, there's a white pine, and that white pine is dead. As a matter of fact, there's a piece of a white pine here that's also dead. And the reason why this is dead is because these white pines are really intolerant of shade. They start out in open field environments, they grow up, they grow fast, but they really need a lot of light. They get shaded in and it kills them. So now the forests that have come up around us, the species, are much more tolerant to these shady habitats. And so they outcompete other species by the shade. So this is one of the mechanisms in which this actually takes place. Okay, so Andres, one of the most important things to do before you start the succession lab is thinking about and knowing the species that you're going to be working with. And we're working with trees for this ecological succession lab. And so trees tell you who they are. You've been here before with me. You understand and know a lot of the trees. What species is this here?
I think this is the red pine, Dad.
This is the red pine. And how do you know this is the red pine?
Because the bark is very thick and blocky.
Very thick, blocky bark, that's right.
And I think that the pine needles are really, really small, right?
No, they're very short and very thick. That's right. And this tree is an evergreen tree. That means it has its leaves right now. If you look up there, lots of leaves on it. None of the other trees around us have their leaves right now. These species, those species are deciduous. So let's walk down here and take a look at this other tree down here.
Let's go.
Sounds exciting, right?
Yeah, I know.
So, what species is this right here?
I think this is the maple.
This is a maple, and how do you know it's a maple?
Because of the bark first off, and because of the opposite sided leaves.
That's right, the leaves are opposite, the bark is thick, it's not nearly as blocky, and it's long and striated, very tight bark. And this is a deciduous species. There are no leaves on it now, but if you were to key it out, or were to find this later in the spring, it has opposite leaves. As a matter of fact, the students keyed this tree species out in the early part of the semester. What's this species right here beside it?
I don't know yet. You know what I think it is?
What is
I think
it?
it's another maple.
It's another maple, and you know why? Because the bark again, but also maple is one of the most abundant species of tree up on the ski hill. What? Wait, what is that?
The seeds?
I think these are the seeds.
No
Wait. Shh. Oh, wait. No,
No,
there's
no.
no toilet paper tree up here.
No. Guys, no.
Now we have an understanding of some of the trees, we understand what we're doing, we need to set up some kind of sampling protocol. And the way we're going to do that is we're going to establish 10 by 10 meter transects, our square quadrats. And within that quadrat, we're going to measure the diameter of all the trees within that 10 by 10 meter plot. And so this typically is done completely at random, right? And so how do you get random? I mean, random is truly a hard thing to do. So one thing we're going to do is I have this red tennis ball. I'm going to turn around, I'm going to close my eyes, and I'm going to throw this red tennis ball, and wherever it lands, that's going to be the right-hand corner of our first plot, okay? And so that's the way we're going to establish this. You know, you throw it over your shoulder, lots of ways to do it, but that's just one way to establish a random direction. There are lots of other ways, using a random numbers table that you use for the Mimicry Lab, but I'm going to first throw this tennis ball over here, and then we'll see where it lands. I'm going to close my eyes when I turn around and see, and that will be the beginning of our plot, okay? All right, here we go. Oh, okay, that's weird. Okay, so it's over here. So let me just walk over here in this first tree. So
Can I join you, Dad?
Yeah, come join me. So here we are. This tree is yet another thing that we haven't seen yet. The bark's a little different. Look, it's blocky and falling. What tree is this?
I think it's a cherry tree.
This is a cherry tree, that's right. Cherry trees are nice, very obvious tree. It has these sort of blocky square bark that flakes off like this, very good. So what I have here, let me walk over to the camera. This is a special type of tape called a diameter tape. It says here, it's made by Forestry Suppliers, it's a 5-meter tape. It's different in that it has a hook on it. And if I pull it out, on this side, it says, here, on this side, it says diameter in centimeters and millimeters. So this is actually not a linear measure. This actually is already calibrated to give you diameter of the tree. It already assumes, the way it's laid out, that you're measuring a cylinder. So that's what we're going to use to measure the diameter of the trees on this transect. So the way we're going to do this is we're going to measure this at, the diameter is taken always in a standard forestry protocol diameter at breast height, which is about 1.3 meters. And so the way this tape measure works, it has a hook for a reason. I'm going to hug the tree. This is the tree huggers thing. I'm going to pull it around, and I am going to hook the tree in here with the hook, and I'm going to get a little closer with the camera, and I'm going to pull this around, and I'm going to line it up with the 0. And so now you can see about the right height. How big, Andres, how big is this, what's the diameter of this tree?
35.
Yep, a little about 35.2 is exactly right. 35.2 centimeters diameter breast height. Okay, so we're going to record that in our data book, right? This is in our plot. The next tree that's in our plot is, let's go to this one right here. Look at this tiny little tree right here. Guess what? We really can't measure the diameter of this little tree, so we really set our low end at 10 centimeters DBH. We don't measure anything that is smaller than 10 centimeters DBH, which is about that size diameter, okay? So we're going to continue to go through this whole plot and measure the diameter, the breast height of all the trees. We're going to be identifying them as we're doing that. We're going to be measuring their diameter, and we're going to do this, we're going to do multiple plots across the entire week for the lab, okay?
Dad, do you know who has a better bark?
Do I know who has a better bark?
Trees or dogs?
I don't know, why?
Trees, because they don't bite.
So trees are kind of boring. What's more exciting than trees are the ferns. Here we have the intermediate wood fern, Rhapis intermedia. You know, I actually have an interesting discovery I made with this. Back a few years ago, I was walking down the trails here, and there were 2 ferns on either side of the trail, and the wind was blowing, and one fern, the wind blew it back, and it blew it forward, and the spores of one fern just covered the other species. It's like all over the other species across the trail. And the wind blew the other way, and that species shot its spores over at the other fern. It covered the other fern with all of its spores. And that's the first time anyone ever recorded a sporophyte in nature.
Just gonna say that joke really was really funny.
Great joke, yeah, right?
Wait,
what is this?
hold up. Isn't this gametophyte in the sexual phase?
No more botanical pornography. How many times have to tell you?
Dang it. Is this the sexual reproduction area of a moth? Wait, Dad. Is this a gametophyte sexual stage?
Let's do that again. Isn't the gamete fight the sexual stage? So the first thing we're going to do in order to set up our plots is I'm going to throw this ball, and wherever the ball lands, I'm going to throw. I have to throw the ball first. Now we need to set up our transect. So to set up, not yet. I have to throw it first.
I missed you.
Okay, so in order to set up our plots, I'm going to throw this ball, and wherever this ball lands, it's